what are called in quantum mechanics observables. And you can probably guess from the word, I think I've mentioned it before, what in physics, what is an observable? Well, it's just a measurable physical quantity, something you can actually measure and get a result from. What are some examples of observables? Well, energy, momentum, angular momentum, spin, charge, stuff like that. Right? Lots of observables in physics. Okay, so here's the definition. What is an observable? Just a measurable physical quantity. Various examples. Now, as we now generalize, we take the ideas we've been talking about, translating, for example, the overlap integral into the bracket, looking on wave functions as vectors, that kind of thinking. As we take that over now and generalize it to other observables, not just position, then then we do start getting new physics, right? Now, I've only got this little bit left in this of the board, this session, but the text asks you to note two things when you as you take over this kind of vector thinking for wave functions. You need to keep in mind these two things. One is when you have a superposed wave function, right? Sigma Cn psi n, that each of these psi n's is to correspond to a particular measurement value of an observable. Now, I'll say that again in different words because it's a very important concept. It's basic to this modern, contemporary, if you like, current way of expressing quantum mechanics. So you have a superposed wave function, right? Psi equals sigma Cn psi n. Each of those psi n's corresponds to, and just saying things a bit differently, each of those psi n's corresponds to a wave function, a state, when you measure it, gives you a distinct value. So in other words, for each psi n, there's a different measurable value. Like, for example, if you measured let's say you measured the angular momentum. Now, I haven't done it yet. That'll be chapter 7. That'll be the next chapter. Also a large chapter, 20 pages. This chapter is the largest in the book, 22 pages. Only about 150 odd pages in the whole course. I mean, one of the reasons I chose this textbook is that it's fairly short. And Davies is he's a pretty smart guy. I don't like his philosophy. I mean, he's not a philosopher, he's more a mathematical physicist. So, anyway. So in the case of angular momentum, you measure its angular momentum and you get a distinct value. And each value, they're different. They're discrete. The angular momenta are quantized. This value or that value. And corresponding to each measured value, the actual number you get for the angular momentum, that corresponds to a particular wave function or state, same thing, right? So these, and like let's say the ith measured value, that would correspond to psi I, the ith state. So when you take a general wave function psi and you expand it, you write it as a superposition of your psi i's, and you're going to measure, let's say, the angular momentum, then for each possible outcome, each possible measurement value that you get, that corresponds to an eigen. I'm jumping ahead a little. each measured value corresponds to a particular wave function, psi n. So you get the nth measurement value. It's the psi n that's the state that you get after you do the measurement. So in a sense, your generalized wave function psi collapses to psi of n, and the probability that you get that measurement outcome, that measurement result, that measurement value is Cn squared. Right? So the probability of getting that the wave function, the superposed wave function psi, it will collapse to psi n, and the new state will be psi n, and the probability that that happens is Cn squared. Okay? I don't know how clear that is, but that's quantum mechanics, right? So that's essentially what this is saying. And well, both these two things. So the measurement results, if you like psi n and psi n, say two of them, if you take the bracket of those two, you get 0. The overlap integral of those two psi functions, if you get measurement m, your wave function collapses to psi m. If you get measurement value n, the psi function collapses to psi of n. And if the overlap integral of those two psi functions, psi m and psi n, is 0. So the eigen, here I go, oops, habit. The wave functions that you get after the measurement, they are orthogonal. Okay? So the overlap integral of the wave function that you get will be orthogonal to any other, and that's essentially what point A is saying. And point B simply says that a general state psi function is just a superposition of these functions. Now, I've been calling them eigenstates. I'll wait for that. I'll come a bit later, future sessions. But these are the psi functions that result from the measurement. So if you get a measurement value that takes the nth possible value, when you have a discrete set of measurement values. So if you get the nth value, that will correspond. The state that the generalized state psi, it will collapse into psi of n. Right? So in general, your psi is a superposition of these psi n's, and these psi n's are the wave functions that correspond to the state, your quantum system, that gives you a measurement value, the nth measurement value. Now, you can see I'm struggling a bit here. It is not easy. It's not easy trying to put into words what quantum mechanics is about. Now, perhaps if I were an MIT or Caltech professor, I could probably do a better job, because I would be smarter. But still, even those, the genius level professors have a hard time putting into words the concepts of quantum mechanics, because the topic itself is difficult. Right? It's hard for human beings to get their brains around the concepts of quantum mechanics. The concepts themselves are not easy. Right? Well, I've now finished the board. This is the 4th quarter, so I will stop there. I'll end with just one comment. If you're studying, or if you're already rather confused, then that's probably not surprising. Now, part of the confusion is just perhaps my way of explaining things. That may be part of the problem. I hope I'm being clear that the nature of the beast itself is not clear. So if you're feeling confused about what quantum mechanics is about, then join the club. It's sort of normal. I'll give you two examples, two famous people, both in quantum mechanics. One, Niels Bohr, whose name keeps popping up. He said, quote, "Anybody who is not shocked by quantum mechanics has not understood it." Okay. And another is Dick Feynman. He was doing his work, great work in the 40s, died in the 90s, I think. He's on record as saying, quote, "I," meaning Feynman, "I think I can safely say that nobody understands quantum mechanics." Right? So I'll stop on that note.